BD similar to University of Washington. I'm sure we will have a few stragglers arriving late, but it is my pleasure to introduce our speaker today, Olivia, who is at the University of Minnesota, where she finished her thesis, and she will be moving to Illinois in a few months. Today, she will talk to us about shifting clusters and social dynamics in non-local approach. Thank you, Olivia.
Thank you. Yeah, thank you so much for the invitation. I really appreciate it. And yeah, what I'm going to tell you about today is actually work that originated from an RU project with two really fantastic undergraduates, Ty and Melindy, who are now graduate students at Melindy's at Brown and Ty is at Georgia Tech. But it ended up being an application of some of the work that Arndt and I did in my thesis work. And so I think it makes a very tangible context for why and how some of those methods would be used. So I'm going to tell you about that today. So I'm going to start by telling you about the context. So about social dynamics, bounded confidence, bias, and about the model that we studied with our RU students. And then I'm going to switch to the functional analytic framework that we used to try to prove some of the things we saw. And lastly, talk about the non-local methods and why and how they came in. I can't change my view on Zoom, so hold on one second. Sorry. Thank you so much. Now I can see all the slides. And so sort of why and how these non-local methods work. So first, the social dynamics context. Social dynamics is a relatively new field of math or subfield. And by new, I mean it kind of became popularized during my lifetime. And it became popular in the early 2000s and centered around the following question: how do people change their opinions? Everybody has opinions, and if we want, we could quantify them numerically, such as how positively do you feel about the weather today? Or how good of a name is the Washington Commanders? Or how bad of a name would the Washington Washingtons be? And so we could assign numbers to these opinions and ask from a mathematical standpoint, how do those change? And there were two related sets of models that were brought forth in the early 2000s, one by Hexelman and Klause, and a related one by Defwant and Weisbach called bounded confidence models. All models are wrong, but I think the important ones capture some kernel of truth. And in this case, the kernel of truth that I think they capture is in this model, agents will talk. So they have opinions and they talk to each other and they compromise, but they only compromise with people whose opinions were close to theirs to start with. Or you can think about it as they compromise with anyone, but they only talk to people whose opinions are close by to start with. And there are many ways to frame this mathematically. In particular, some of the differences between the formulations of the models were like whether or not they were agent-based or stochastic in time or regularly distributed in time, but then randomly select the agents, things like that. But the model we studied in the RU is a deterministic version of this model set on a lattice, and it is as following. So what is being modeled is the distribution of opinions. So n represents an opinion, and we let n be an integer. So it is unbounded in either direction and integer valued. And Pn represents the population at opinion site n. Or if it's a distribution, you could kind of think of it as like the fraction of the population or the continuous population. So Pn is not a number of agents, but a continuous variable. And how this evolves is people at n minus 1 and n plus 1, those will compromise. And from there, you will see an increase at Pn. On the other hand, people at n talk to people at n minus 2 and n plus 2. And so you see a decrease at n based on those rates. And what the confidence bound here is 2. So the agents will talk to people within 2 opinions. And they don't talk to people one away just to preserve discreteness. If you simulate this model with wider confidence bounds, it looks very similar phenomenologically. So this one is sort of like the simplest one you could write down in some way, not in every way. And it has some properties that we would expect. So conserves non-negativity, total mass, center of mass. You could have infinite mass in this case, but going to sweep that under the rug. But this model is extremely well studied and has some phenomena that are fairly well known. And I think one of the reasons it became so popular is not only on the mechanism level does it kind of resonate with us, but on the level of what happens, it also seems to resonate. So the model has a number of steady states. For one, the uniform distribution, where there are an equal number of people at each opinion site, is a steady state, because the number of people compromising in every direction will be the same. And then you can have opinion clusters. So if everybody is at one opinion or consensus, there's no one to talk to. So that's a steady state. Similarly, if you have people at 2 sites, that's also a steady state because they're still too close to talk to anybody. And you can have multiple of these clusters as long as they're sufficiently spread out. And if you take the uniform distribution and add small random perturbation to the initial condition, pretty quickly, you see formation of clusters with fairly regular spacing. And people have studied how that relates to the confidence bound and a lot about these dynamics. So we see formation of these clusters of opinions. And what we wanted to study in the RAU project was adding bias to this.
Can I ask a question?
Yeah.
On the previous slide,
Yeah.
where you had the 2-site cluster, if the 2 sites are within 2 of each other, then why would that be a steady state?
If they are like next to each other, so only one apart.
So
the
why could one opinion not eventually overtake the other opinion?
Okay, so that would happen if you had interaction between neighboring opinions, but in this model, we only consider interaction exactly the way just to preserve the discreteness, because otherwise we couldn't have like compromise of those two and you would the greatness of the model.
Okay, thank you.
But we did look at a version where we had those interactions as well, but that is outside the scope of this talk. So yeah, so we wanted to look at adding bias to this model. And this has already been studied in many ways. In particular, people have studied varying the width of the confidence intervals. So some agents are more or less certain of their beliefs. Asymmetric confidence intervals, where maybe you'll listen to people more on one side than the other, or farther on one side than the other. People have studied if you have stubborn agents, so some agents that don't compromise at all, including people have modeled advertising or even propaganda through modeling that as a stubborn agent or something that does not change its opinion. And people have also looked at algorithmic bias, or if you're more likely to interact with people closer or farther to your opinion, what happens? But the question we had was a little bit different. These are all questions about the compromise mechanism itself, but they don't affect well-formed clusters very much, because these are all sort of in the compromise process. So our question was, does there exist a bias term that we could add which would cause a coherent movement of these clusters? Sorry, parties is a typo. We used to call them parties, but now we call them clusters because we don't want to actually model anything real. Not really, but we're not really modeling like parties per se, just clusters of opinions. So before I tell you what we did study, I'll tell you what we didn't study. The first bias term we added was of this form, and it is called, perhaps uncreatively, linear bias. And that says that at opinion at any given time or opinion, an agent will jump from site n to n-1 with probability beta, independent of their opinion, independent of the population at the opinion. Just every single agent with some small probability would become more extreme. This you could think of as coming from external factors, or there's just something in the air that's making people jumpy. They want to become more extreme. This is similar to the discrete diffusion studied in a paper by Eli Ben Naim, but this is like only one-sided. They're only going to change their opinion towards one extreme. And when we simulate that, what we see is we do see movement of a cluster, but it spreads out. And the question we really wanted to look at is, does there exist something that will make a cluster move but stay together? So this didn't seem to have the phenomena that we were looking for. On the other hand, this is the term we did end up studying, and we called this either quadratic nonlinear bias, or we called it self-incitement. And the interpretation of this term is this. Rather than a fixed probability beta, an agent would jump their opinion from n to n-1 with probability beta times Pn. So the more people there are at a given opinion, the more likely they are to become more extreme. This had inspiration mathematically from nonlinear diffusion, because nonlinear diffusion preserves compactness, unlike regular diffusion, but it also had motivations from sociology, because this is a phenomenon that people have actually noticed in humans. In about the 1960s, it was noted that people, when you got them in a group and asked the group their opinion about something, their answer will be more extreme than if you asked them each individually and averaged it. So there's some truth to the fact that a group of people will kind of rile itself up and cause the group as a whole to get slightly more extreme. That phenomenon is named group polarization, and there's a lot of hypotheses as to what causes it, but it's well studied, but not necessarily fully well understood. So for those two reasons, we decided to look and see what this term would look like. And this time, when we simulated it, we saw more of what we were looking for. The cluster of opinions seems to move, but stay together. It's not really spreading out. And when we increased the bias term, we started to see something interesting. So for one thing, note that the speed goes faster. But for another thing, we see the cluster, it gets a little flatter, and it also starts to sit atop this like bed of opinions that the traveling state that we see is on top of a uniform state. And then when we let beta be greater than 2, notice something really weird, which is that the cluster seems to die over time. It doesn't look like that it is, but it does eventually, not in finite time, but like eventually would die off. And that was like, wait, what? And so if at any point in the rest of the talk you get bored or lost, I encourage you to think about like, why would that happen? Why would too much bias cause breakup of a group of opinions? And we have our thoughts about it, but there's not necessarily one right interpretation of it. However, one also gets excited when one sees this because, in other words, the linear state seems to have regained at least marginal stability, and one can affirm this with linear analysis. And so we have a state that at past a certain parameter ceases to exist, or in other words, going backwards, starts to exist at small amplitude, which from a bifurcation theory standpoint is like, this seems like something we could study. Also numerically, you can ask MATLAB if it thinks there would be a traveling profile by transforming the equation into a zero of a functional equation, and MATLAB thinks there is up until beta equals 2, and the profiles look like what I showed you in the direct simulations. So they start out pretty sharp and they get flatter and sit atop a higher and higher bed of opinions. Now, in the two perturbative regimes, so in the two regimes, beta close to 0, beta close to 2, the first really natural one to study is the one for small bias for beta close to 0. So I'm dedicating one slide to what we tried to do and why it didn't work. For beta equals 0, the set of two site opinion clusters form a 1 or 2, depending on if the mass is included, parameter family. Meaning you could have the opinions on the two sites be distributed any amount between the two, and you could think of kind of moving the mass along, and that forms a continuous family of steady states. And for beta greater than 0 small, moving clusters kind of follow close to this family. That in the first simulation you saw, they kind of stayed pretty close. So looking at that, one would be really tempted to use singular perturbation theory. However, there turns out to be some pretty significant technical difficulties when trying to do so. For one, the family isn't smooth. So every time the cluster moves to one site and then starts adding on to another, it forms a corner where it's not, the tangents have a jump. And additionally, at any given cluster, linearization has an infinite dimensional kernel. So both of these kind of provide a pretty significant challenge to using Fenechel theory because on the one hand, we have like infinite kernel directions, which are not all the directions that we want. And then we also don't have a smooth family, so you can kind of only do it for a small range. But locally, you can still use these ideas to study what happens and compute expansions for the speed, and find for small beta that the speed of the cluster is proportional to beta. So now what we did do. So for beta close to 2 or close to onset, our perturbation theory spidey senses go off and we're like, okay, we would like to use perturbative methods to try to prove that a traveling cluster exists. So functionally analytically, we rewrite the equation as a equation for a continuous fixed profile moving through the lattice. Now n is an integer, but CT is continuous. So it's a fixed continuous profile moving through a discrete lattice. And if it helps to visualize it, here in this visualization, blue would be the profile and red is what you see along the lattice points. So on the lattice, you see kind of this like jerky movement, but the profile itself is a continuous profile that's the same. And when we write Pn is Q minus Ct, shifting to a traveling frame, we get this equation for Q. This equation is called a forward-backward delay equation because we have that the change in Q depends in some sense on both the past and the future, on Q at x minus 1 and at x plus 1. This equation is also very nonlinear. All of the terms except for Q prime are quadratic. Because of that, using any type of linear analysis is going to be difficult. However, we know something about the solutions close to onset. They are close to the uniform state. So we rewrite Q equals 1 plus little q for Q small. And doing so, we get this equation, which doesn't immediately look very different, but what's different is that we have a number of linear terms that are delay terms. And then we still have quadratic terms as well. Formally, you can, in the style of Guido Schneider and Jean Wayne, let Q equal Q of epsilon n minus ct epsilon cubed t. So you can scale time and space and derive formal amplitude equations, which are not rigorous, but when you do that, you get the purple terms at leading order and the blue terms at the next order. The purple terms are, yeah?
What's the motivation for the epsilon cubed time scale?
Experience.
Okay, that's a very common answer with motivation theory.
This is not actually the main thing we did. So this is just what put us on the trail. So fear not, this is not the bulk of it. This is
if you try epsilon squared, then it doesn't work, or I mean, like
I don't remember
Schneider tried cube because they were looking at the KDV type regime.
I don't remember offhand, but
Okay.
I know that this is what like made things work out. But at leading order, you get KDV. And at the next order, kind of have two terms, like a negative damping and fourth order dispersion. And so those kind of like have opposite sign. But the KDV in particular has spike solutions. It has solutions that look like what we're looking for. So this was like, okay, wait, this might actually have the behavior that we want. But this is not a rigorous proof of existence because it's a formal amplitude equation. You would have to prove that these are, in fact, like that this gives the behavior of the equation.
Okay, thank you.
Yeah. So before I say the way we went about the proof, first, just like a very brief overview into the main idea. So from a dynamical systems point of view, one of the main tools used to reduce the dimension of systems is invariant manifolds. And what this is if you have some kind of ordinary differential equation, U prime is f of u, and you have a known equilibrium, frequently you're looking for some solutions which might have some behavior. Maybe you're looking for solutions that grow exponentially or decay exponentially, or if you're looking for solutions that are bounded both in forward and backward time, you're looking for like bounded solutions. And when you're looking for solutions with particular behavior, we can decompose the space near the equilibrium into spaces which on the linear level correspond to either growth, decay, or neither. That is positive, negative, or zero real part of the eigenvalues. And then there are theorems that say that the eigenspace in linear flow will correspond to an invariant manifold in the nonlinear flow. And in general, for exponentially growing and decaying functions, that behavior will generally persist in the nonlinear equation. But for eigenvalues with real part 0, it's not known either way, and you have to actually look at the reduced flow to figure out what happens. So what people will do is take the whole equation, reduce it to a lower dimensional center manifold, center because it's the 0 eigenspace, the things that neither grow nor decay exponentially, and look at that flow specifically there to figure out what happens. So some work that my advisor and I have done in my thesis is looking at invariant manifold techniques instead of for ordinary differential equations, for equations that are of non-local type. So what do I mean by that? Well, a non-local equation, I mean an equation involving a spatial convolution. So it might have time dependence, but the shifting to a traveling frame, you would eliminate that dependence looking for steady states of an equation involving a convolution kernel K star U. And we can actually rewrite this delay equation as a non-local equation in the following way. We can rewrite a delay term as convolution with a shifted Dirac delta. Because we know that the Dirac delta is the identity for convolution at x. So to get a delay term, we just shift the delta. And when we do that, we can rewrite the equation in this form. And we wanted to do that because this is the type of equation that my advisor and I have looked at in some of my thesis work, and the theorems about center manifolds originated in 2013 with my advisor and Greg Fay, who did this work in H1 function spaces, H1 based function spaces, and what we did is shift to C0 based function spaces to study a slightly different, to get greater regularity of the manifold. That's not important for this example. But what it says is that under sufficient hypotheses on the kernel and on the nonlinearity, the non-local equation has a center manifold at the trivial state. And if you're paying attention, you might notice that this equation and the equation on the previous slide are not exactly in the same form, but if you precondition with the inverse of the operator, that is c d by dx plus 2 beta plus 1 times the identity, then not only does it get in this form, but it also then makes the kernel smooth enough to satisfy the conditions. And the upshot of doing this is on the center manifold, you get a finite number of ODEs which describe all small bounded solutions to an equation that's posed in an infinite dimensional Banach space. And you can get these ODEs by writing the center manifold as a graph over the kernel of the linearization. One slide on why we do this. For one, as I will claim, in contexts like this, and even for ODEs, the computation that I'm about to show you provides a computationally simple method of finding the reduced vector field. But also, studying these types of equations covers the case of infinite forward and backward delay, because previously center manifold existence was treated by Jooss and Kirschgessner and others for finite delay. The computations are more local, involving changes of coordinates, and they are generally very involved, and but existence has been treated. So the motivation was also to cover the case of infinite forward backward delay, where you really can't have any phase space because like the change at a certain time depends on like all of recorded history and the whole future. So those are the two reasons why one would want to do this. Now one slide on why it works, and the rest is a claim that it is a very doable thing to find such an expansion. Why it works. So in a standard center manifold computation, you write the center manifold as a graph over the center eigenspace. Then you Taylor expand the graph, and you take the flow on the graph in the whole space. Lastly, you project the flow on the whole space down back to the center eigenspace, and you get a reduced flow on the center eigenspace. And what we do is really the same thing. So if you think about it, what is the center eigenspace? Well, it is the kernel of the linearization, the things that get mapped to 0. And we could still write the center manifold as a graph over that space, provided it's finite dimensional, which it has to be for the theorem to work. And then we could similarly take the flow and project it. To do that, you need a flow. But if one thinks about that, what is the flow? Well, the flow says take a solution and shift it to time t. On the level of the function, that is the shift. It says shift your solution by, in this case, xi is what I have written. And if we think of that as the flow, we can consider that action and consider that action on the graph and project it, and we get a reduced flow on a finite dimensional space. Sorry. There, I thought I had more text, but I didn't. And once you have a reduced flow, you can differentiate to get a reduced vector field. And on the whole, this feels very weird. Like it feels strange at first to think about it, but if you think about it, it all kind of like it all does fit together. It's just one doesn't typically think of the flow as a shift or think of this in a function space setting. Now, the work of the theorem is in proving the existence of the manifold and that it can be written as a graph tangent to the kernel of the linearization. But that work is done in proving the theorem, so once you have all the hypotheses, what remains is really doing the computation of the reduced vector field. So I'm going to do an example, which is not the social dynamics example, but I'm going to do this because I want to be able to start and finish it and see how it works. And then we'll come back to social dynamics and see why it's really the same. So the example I'm going to do is a fourth order ODE minus u fourth derivative plus u second derivative plus u cubed equals 0. And if you protest that this is really, really definitely not a non-local equation, that's fair. But we could turn it into one if we really wanted with use of a Green's function. But also what's nice about this is that you don't have to do the computation in the non-local form of the equation. You can do the computation of the center manifold in either form of the equation because it's invariant in both senses. So how do we do it? Well, we start by computing the linear kernel. So the functions that are mapped to 0 by the linear part of the ODE is the constant functions and linear functions, so the span of 1 and x. And then we're going to write the kernel element. We're going to parameterize it. So u equals a plus bx. And then we're going to seek a Taylor expansion of the center manifold. And this is in terms of a and b, so we're parameterizing it over the kernel. What may seem strange is that the Taylor coefficients are functions of x. But if we can do this in really high-dimensional finite vector spaces, like why not do this in function space? And so we write this expansion, and then we do the same thing we would in ODEs, we use invariance. So we plug in the manifold to the equation, and we get this. Now, a plus bx cubed from the nonlinear term, secretly the manifold is also plugged in there, but that is going to give us higher order terms, so I didn't put that on the slide. From the linear parts, we get the linear part acting on the third order terms, and then we have the kernel in the nonlinearity, and those are going to have to be equal. So actually, these Taylor coefficients, which are functions, are polynomials because a plus bx cubed gives us a polynomial. This is not really just unique to this though, because typically in a center eigenspace, the functions in it will be either polynomials or polynomials times sines or cosines. So the Taylor coefficients we look for really just match the form of the functions in the kernel. So we can make an ansatz for each one, and we just match coefficients. So for the a cubed term, we are looking for a function whose second derivative minus its fourth derivative is 1. That function is x squared over 2. For the a squared b term, we're looking for a function whose second derivative minus its fourth derivative is 3x. So for that, we get 3x cubed over 2. For the ab squared term, we now have 3x squared on the right-hand side. This one I couldn't do in my head, so I made an ansatz. And I used a fourth and second order polynomial, and you take the derivative, set the coefficients equal, you get x to the fourth over 4 minus 3x squared. And lastly, for the b cubed term, we just have b cubed on the right, or sorry, b cubed x cubed on the right. And I tried a fifth and third order polynomial, got these coefficients, and got x to the fifth over 20 minus x squared. So from invariance, we get our Taylor coefficients at third order. And you could keep going to higher order by taking our third order approximation, plugging that into the nonlinearity, and using invariance again. And again, we'll have more polynomials, but in this case, I stopped at third order, but you could do more. So now that we have the manifold, what is the reduced vector field? So the first step was finding the expanded manifold, and the second step was take the flow, project the flow. So the flow was the shift action. So we're going to plug in x plus c for x to find what the shift action does. And then we differentiate in c. in reality, you can project and differentiate in either order. So I thought it was easier to differentiate than project, but either order works because they're both linear. So we take our Taylor expansion, plug in x plus c, differentiate at c equals 0, and we get this. And then we project. So to get the a term, we project onto constants. We look for all the constant terms. And to get the b term, we project onto x. And so our reduced system is two-dimensional. We get a prime is b prime is a cubed minus 6ab squared. And that is our reduced system, which in this case, we just reduced it from 4-dimensional to 2-dimensional. But in the non-local case, we're reducing it from infinite dimensional to finite dimensional. So back to social dynamics. Why is this really the same? So we really follow the same steps as we did for the ODE. Again, we can do the computation in either form. So here we just use the form before preconditioning because we found it easier. We look for the linear kernel. So we find that's the dispersion relation, and we find a multiplicity 3 root nu equals 0 at the critical parameter values. So the kernel is 3D. In this case, we do have a parameter. So what happens to our expansion is we just also expand in terms of the parameter close to, like, after shifting the value to 0. So in this case, it's the same thing. We get that the kernel is constants, linear, and quadratic functions. We parameterize the kernel, and we seek an expansion of the kernel as a graph. We seek an expansion of the manifold as a graph over the kernel with the parameters as additional things that we're expanding in. And again, we use invariance. So again, because our nonlinearity is, because our kernel is polynomials, when we plug those into the nonlinearity, we get polynomials. And if your nonlinearity was not simply a polynomial itself, what you would do then is just Taylor expand that as well. And so again, we try as an ansatz polynomials of the order just above the kernel. We plug that in to the equation and match coefficients. So on the one hand, we have the kernel plugged into the nonlinearity. On the other hand, we have the linear parts applied to the Taylor coefficients. And we get the following equation, and we just match each of the terms. So for A0, A1, we get this relationship, and we get the Taylor coefficient for that is minus x cubed. In this case, it was slightly more involved, and I have to say I was extremely impressed with our REU students because they managed to compute these correctly by hand. And they checked them with Mathematica because, as you would be, they were pretty skeptical, but they did in fact compute these. And so again, slightly more complicated, but still polynomials. And in the same way, once you have the expansion, plug in x plus c, differentiate and project, and we get 3 ordinary differential equations that describe the dynamics of bounded solutions. So if a bounded solution exists to the original equation, then that corresponds to a solution that is bounded of this 3-dimensional system. We can massage this system a little bit. So first, we would like to reduce the dimension to 2. So by using conservation of mass, you can reduce the dimension by finding a certain expression that is conserved. And then you can rewrite that as a second order system. And you can also get rid of the O of 3 using a smooth coordinate change. And at leading order, you get the same reduced equation that we got from the amplitude equations. So that's kind of exciting. And so now we have a solution for beta equals 0, that there exists a spike or homoclinic solution, and using a Melnikov analysis or the implicit function theorem, you can show that for beta tilde positive, there is still a solution. So rigorously, there exist spikes close to onset in the system. And just to show you how much we still don't understand, what I'm about to show you is kind of was a brief investigation into what happens in the wake of these traveling spikes. Now, the uniform state is not stable when there exist spike solutions. So we don't expect stability in an absolute sense. But one can ask, okay, in what sense might we have stability of a traveling solution? And one sense that you can ask is, could you have convective instability versus absolute instability? So does your spike kind of outrun perturbations behind it, or do they go at the same speed? You can try to answer this question by looking at linear spreading speed, so asking on the linear level, what should a small perturbation spread at? And if you look at the linear spreading speeds, then that is always less than the speed of the cluster, but that doesn't always tell the whole story because sometimes perturbations can travel faster. So what you're about to see is simulations of just in the wake of a moving cluster, what happens. So the cluster is not shown because it's a lot bigger. You're just seeing what happens in the wake. And what happens is, for a while, things propagate at the linear speed, but then from the initial perturbation, there kind of grows this like really big spike that like eats all the other ones and runs. And that appears to travel faster than the linear spreading speed, but not like up to, but not greater than the speed of the traveling cluster. Also, this appears to happen for every beta that we looked at. It just takes different amounts of time to happen. So we just saw him take off and then break the computer up on the left, and the right bottom one's still going. So this is very strange, and if anyone seems to have any insight onto this behavior or has seen something like it before, let us know of basically a pushed front overtaking pooled fronts in the wake. But to sum up, we propose self-incitement bias as a mechanism for coherent movement in social dynamics. So this kind of self-incitement seems to be important for having coherent movement. And we did simulations with other similar terms, but what seemed to be the connecting factor was whenever there was this self-incitement or the probability of extremism, or not extremism, but getting more extreme, increasing with the population, it seemed to be key for having coherent movement. The non-local center manifold expansion provides an algebraically simple, or I guess I should say calculusly simple, reduced vector field computation, which can be used for finite or infinite forward-backward delay equations. We find that strong bias causes the uniform state to regain stability, which is kind of, it surprised us for sure. My personal interpretation of that is that when the bias is too strong, you might get like people becoming extreme so fast that the people aren't compromising with them anymore. That if you wake up and you're friend has started a extremist group about something, you might not be like really willing to compromise anymore. So that's my personal interpretation, but I think there's many ways to think about it probably. And further directions, as beta to 0, that would be a really natural regime to look at, and we would love to find some way to make a perturbative argument flows for coherence. Although current sort of Fenichal methods seem to not be quite built up enough yet. Stability/instability of the spikes, weird things seem to happen. And to look at other mechanisms for coherent movement. And on the analysis side, we're looking at how tight we can make the assumptions on the convolution kernel so that such results can be applied in as many cases as possible. Thanks for listening, and let me know if you have any questions.
Okay, we have time for questions.